Next, we have invited talk by Fedorov Aleksey, Head Institute of Physics and Quantum Engineering. Dr. Fedorov Aleksey is the head of Institute of Physics and Quantum Engineering at National University of Science and Technology, MISIS. He has an Information Security Engineer degree from Bauman Moscow State Technical University. He also has a PhD from Paris-Saclay University, France, in physics and mathematics. In 2020, at the age of 26, he became a professor at the Russian Quantum Center Department of the Moscow Institute of Physics and Technology. In 2021, he won the Fidelity to Science Award for his contribution to popularizing science and technology among young scientists. In 2023, he became a member of the Coordination Council for Youth Affairs in Science and Education of the Presidential Council for Science and Education. I now welcome Sir to start his talk.
Yes. Hello, and thank you very much for so kind introduction. So let me try to share my screen. So can you? Thank you very much. And I was asked to focus more or less on our activities related to quantum cryptanalysis and developing quantum-resistant cryptography tools. So basically, it's more or less well known that quantum computing possess one of the threats on the currently existing cryptographic tools, especially ones working on cryptography based on public keys. And in this regard, we work in several directions. So first, we, with our colleagues, develop quantum computing devices and try to push the limits of their performance. Then we worked on cryptanalysis. So we worked on creating new types of algorithms for quantum computers that allows use them for analyzing security of cryptographic algorithms. And finally, we developed several directions in quantum-resistant cryptography. So on cryptography, which believed to be useful and believed to be resistant, even having in mind that our adversary has a powerful quantum computer. So I will first start about our activities on quantum computing. And maybe one of the key points that we explore here is the fact that we use qubits. Qubits are multi-level quantum systems. And this is related to the fact that in classical information theory and in classical information technologies, we are heavily based on binary information encoding. So we have basically 0 and 1 as main paradigm bits that we used everywhere. However, quantum processors, which we used in our current experiment, allows us to encode information in much more rich structures with many energy levels, which means that we can use them not for binary encoding, but for much more complex encoding systems. And many platforms that are now used to build the quantum computers are actually helpful, and they allow one to encode a system in a much more complicated way. So here presents several examples of quantum processors that are now under the development in Russia based on superconducting circuits, atoms, photons, and trapped ions. And all of these systems can be used not only for binary qubit encoding, but also for qubit encoding. And the crucial question here, whether we can get some advantages by using these systems in the qubit setup. And there is a large progress in this direction across the globe. So many institutions work on building quantum computers with qubits, for example, based on trapped ions with up to 7 controllable levels. So instead of 2, we have 3, 4, 5, 7, and more in United States, in China, and there is a large portion of scientific activity around this direction. So we also worked on that experimentally, and that's our joint work with my colleague Ilya Semeryakov, who built in Russia multi-qubit quantum processor, where we use 10 ions, 10 qubits, in order to perform quantum operations. And the basic idea that part of these operations we conduct not between two different ions, but inside one physical ion. And we use ytterbium ions with many, many levels. And we have such ability in our experimental setup. So that's how it looks like now in practice. So that's the most powerful quantum computer built up to now in Russia with 20 qubits worked on qubits. So each shining dot here on the screen is individually controlled trapped ion, which we can use for encoding information. So one of the things that we would like to do with a large-scale quantum computers is actually factoring. Yes, so finding prime numbers with quantum computing system which automatically possess a thread on a quantum computer. So in this activity, based on the idea of using quantum technologies to break cryptographic algorithms, has already like more than 30 years. And it starts from famous algorithm proposed by Peter Shor in the middle of 90s. Unfortunately, this idea, based on the direct application of Shor algorithms, required prohibitively large amount of qubits. So as I mentioned, we work with dozens of qubits now, but in order to break cryptographic codes with quantum computers, we need millions of qubits. So millions, which, much ahead of what we can do now. That's realistic estimations that in order to factor 2048-bit RSA integers in 8 hours, we need about 20 million of qubits, assuming that we do error corrections with the parameters that are presented on the slide. So that basically means that in principle with quantum computing you can do so, but it's hard to imagine when we will get such a quantum computer in practice. There are, of course, other attempts to optimize that. For example, recently, several papers were published on arXiv related to reducing the resources that would be needed to use factoring and computing discrete logarithms with quantum computers based on optimization of the Shor algorithm. And that's mainly done by Regev and extension of his work, but still it's currently non-clear would it be lead to improvement in the physical implementation and how many qubits we will need, and raw estimation, and still we need hundreds of thousands of qubits or so in order to implement such quantum algorithms. And very recently, about a year ago, a couple of years ago or so, a large group of scientists, they proposed to use currently existing and upcoming generations of quantum computer in order to factor. And they demonstrated that with the use of combination of classical Schnorr's algorithm, so don't to be mixed with Shor algorithm, and quantum approximate optimization, one can get significant improvement in factoring with less amount of resources. So basically, so they estimated that with quantum computers of about 400 of qubits, it would be necessary to break RSA algorithms of the more or less existing standard. So that's, of course, was sensational announcement, and we started to go deeply and deeply to understand what's going on. So it works like that with classical Schnorr algorithm, we selection a factor base, finding smooth pairs, so-called SR pairs, construct linear system of equations with that, and construction of factors from these solutions is based on just Fermat's approach. And the problem is that the search was this as SR pairs, they can be done as solving shortest lattice vector problem, which in turns can be solved with so-called LLL algorithm. But that requires significant amount of resources. So what has been suggested is to reformulate this problem as quadratic and constrained binary optimization problem and use quantum computers to solve this optimization problem. And the assumption is this factoring can be accelerating with when this SVP problem, shortest lattice vector problem, is solved by quantum computer. So that's in more details how this quantum approximate optimization algorithm works. So basically you prepare some quantum state and then optimize it unless you will get the solution. And solution in this case is just this vector that we need in order to factor. But as we realize, it seems that it doesn't work mainly because of many pitfalls that exist in this algorithm, and we demonstrated it. And also recently, colleagues from Google also, pointed out that this approach would not work. So one of the things is that this classical feedback loop sometimes kills all the potential advantage that we have, and sometimes we don't see even any convergence of these algorithms to the solution. So you see here that this doesn't go to 0. So so basically, random search in this case becomes more efficient rather than this approach. So seems it is not scalable. So I would not go deeply into details. If you're interested in, I would be happy. But in our paper, we summarized and formulate the main results of our analysis. So in which concrete cases this would not work. So what we propose to do in order to make it better, we propose to kill this classical feedback and basically use these algorithms in a bit different way when we used these parameters that we need in the algorithm by calculating on the training samples and a unitary evolution algorithm, which makes this approaches much more efficient. And by that, we demonstrated it experimentally that for small scale quantum circuit, we can use about 10 qubits in order to factor about 1,000 scale number. So my point would be that this approach in general can be saved, but still needs to be investigated. And there's still the question about the amount of the resources that would be need in order to factor something realistic is needed to be further investigated. But it's interesting avenue. So here we demonstrated that we work with better than random sampling and work with even larger numbers. So about our activity about quantum resistant cryptography. So I'm not really sure how much time actually I have. So from organizer, I heard that about 10 minutes or so. So I'll use the rest of my talk just give a brief overview what we have. So first, we developed a high-speed quantum key distribution system, which use single photons in order to encode information and send it between receiver and transmitter. We demonstrated the full security of this protocol by presenting a security proof. We demonstrated the level of practical security, so basically the absence of side channels with these devices, jointly with Vadim Makarov, who is known as quantum hacker, the guy who is able to hack even quantum things. Best possible post-processing procedure we developed by our team, and still it's a record in efficiency for certain aspects. And we have simple version of this device for research, development, and education. So we work intensively of building quantum networks, so connecting different, devices connected via infrastructure, and we created some switched-based network system which allows to reduce the amount of resources that is needed to build such quantum network. So we also worked on space quantum key distribution. So we already launched a transmitter prototype which allows to send the signals from the basically space to ground, and work now on testing it and connecting with this device from the space. So the basic idea is that this satellite can be used in order to send information for generating quantum keys. And finally, so let me mention that we also worked on post-quantum algorithms. So post-quantum algorithms are actually classical algorithms that are resistant and against the attack with quantum computers. And we have fully integrated library compatible with OpenSSL containing the best currently existing quantum resistant algorithms. And these things can be used in any platform and already can be tested. And also we have like solutions based on that, for example, tunneling of the traffic using post-quantum algorithms for browser extension, proxy service, reverse proxy, and things like that, which can be integrated in any also IT application that we have. So basically, I believe that we live in the very interesting period of time when we understand that quantum computers are progressing, and with these capabilities, indeed, classical ways of securing information needs to be reconsidered. And there are two approaches which we find complementary. On the one hand, quantum key distribution, which will be great for securing information, for example, between data centers and some critical infrastructure, and post-quantum algorithms, which can be easily integrated in any user applications. So that's basically what I would like to present it, and let me go to the the most important slide of my talk. Thank you very much for your attention.
Any queries are there? Okay, so there are no queries. Thank you, Aleksey.
Thank you very much for attention, and greetings from Russia. So have a nice conference.
Thank you.
Thank you.